The last category that we're going to learn how to name are acids. These are, we can think of them as being related to the ions. They are molecular compounds. They are not ionic in nature, but when you put them into water, they ionize and form ions. So they're kind of in between. We recognize acids because their formulas start with hydrogen. All the acid formulas we're going to deal with start with H. And we recognize them from their names because they all have the word acid in their name. It's really nice. Nobody has trouble remembering these. There are, again, two groups. So we have binary acids and oxyacids. Guess how many elements are in a binary acid? Two. So we've got hydrogen and a nonmetal. That's all. And oxyacids, what do you think those have in them?
What? Oh, oxygen?
Oxygen. Okay, they're going to have hydrogen and a nonmetal and oxygen. So the oxyacids have oxygen, the binary ones do not. And they've got two different systems for naming them, and that's why we need to identify them as being different. So there's a graphic showing you binary versus oxyacids. So the binary acids, two elements, hydrogen and another nonmetal. And the pattern here is we put the word or the prefix hydro in the beginning, and then the base name of the other element, we change the ending to ic, and then we add the word acid. So these guys also have two names, but they all have the same last name. They all end in acid. So here's some examples. HCl, this is a binary acid. We've got hydrogen and we've got chlorine. So we put the prefix hydro, and chlorine becomes chloric, and so this is hydrochloric acid. Now some of these acids have other names as well. If you have a swimming pool, you may have purchased muriatic acid at the swimming pool supply store. That's the same thing, it's HCl, it's hydrochloric acid. Question?
What's the AQ for?
That's a good question. AQ. So AQ means that this is aqueous, it's dissolved in water.
Okay.
Some of these acids are, HCl, pure HCl is in the gas state at room temperature, and it's named as a binary molecular compound. It's hydrogen chloride. When it's dissolved in water, it ionizes and is an acid. So your book is going to be pretty consistent about showing these formulas with AQ, because technically if it doesn't have AQ after it, then we name it as a binary molecular compound. If it has AQ, we name it as an acid. In Chem 20, I'm not going to get hung up on that. We're just going to call them all acids, but that's why they have the AQ back there, because we should. HBr, another binary acid. So hydrobromic acid. So HCl with a G is hydrogen chloride. In the gas state, that's not the acid. So what about this guy? H2S. Okay, he has 3 atoms, but it's only 2 elements, hydrogen and sulfur. So it's hydrosulfuric acid. So examples. I really need to edit these examples. So HF. It's a binary acid, right? Hydrofluoric. There's no flour in this. Hydrofluoric acid. There's no flour in fluorine. Okay, that's the common misspelling, OU. That seems more normal, but this is chemistry and we do things backwards, right? So it's UO. Hydrofluoric acid. How about this last one?
Hydrosulfuric?
Hydrosulfuric acid. Hydrosulfuric acid. Any questions? I think we need to do an example because I don't think they have one coming up next. Nope, they don't. We need to do an example of writing formulas from the names of these guys. So if we had, what if we had hydroselenic acid? Well, from that name, we see that it's a binary acid. It's going to be hydrogen and what element? Selenium. So how do we know how many H's and how many S's? We have to look at the charges. Hydrogen, when the acid ionizes, is going to form an H+. And selenium is 2-. Good grief. So then we do the same ionic thing with the crisscross, and we end up with the formula H2SE. That's why hydrosulfuric acid is H2S. Sulfur and selenium are in the same group. They're both -2.
How do we know to put the AQ or not? Like,
Well,
I don't know if it's going to dissolve in water or something.
If it's named as an acid, it's aqueous.
Okay.
If it's named as a molecular compound, it's a gas. But again, I'm not going to try to trip you up on that, but good point.
Is there a way also to define from that as, like, since it's H2SE, would that define its strength of that acid?
No. So the oxyacids, it's a little bit different. The oxyacids have oxyanions in them, and we just talked about how we name all those things. So here, HNO3, these oxyacids are going to be an oxyanion with hydrogens on it, hydrogen ions. So this is NO3 with a -1 charge, so the acid has an one H+ on it. Sulfite has a 2- charge, so when we make an acid with that, it's got 2 hydrogens. Sulfate is the same. So the number of hydrogen ions depends on the charge of the oxyanion. So we look at the name of the oxyanion, and that forms the basis for the name of the acid. If the ending of that oxyanion is "ite," then we get "us" as the suffix. If it's "ate," we get "ick." You're like, how am I going to remember that? Well, let's put it in. So I have a silly sentence for you. Hopefully I can write this without, I'm going to give up on that and just use my finger. But my finger works better. Okay. Rick ate him before he could bite us. How's that for silly? This is like the horses need oats thing. Okay, so here's the ick. Ick and ate go together. If the name of the anion ends in ate, like nitrate or sulfate or phosphate, you change ate to ick. So nitrate becomes nitric acid. sulfate becomes sulfuric acid. And ite goes with us. So if it's sulfite, then it's sulfurous acid. Okay, Rick ate him before he could bite us. So here's a table that gives you a bunch of the names and, color codes them and everything. And so like here, acetic acid. Come on, pointer. Where are you? There you are. Okay. H2C2H3O2. Like, wow, that looks big and complicated. Well, cover up the H's, and what does that look like? That's acetate ion. I made you memorize that one. So this is acetic acid because it's from acetate. We change acetate to acetic and add the word acid because it's from this ion. Okay, so we have to recognize those polyatomic ions in the acids. Cover up the H and see what's left. If it's got oxygen in it, then do Rick ate him before he could bite us and change the name. So there's got to be some examples here. No, just a big old table. That's nice and all. So, go look at that later. But we need some examples with these acids. Like, how can you just drop that on someone, right? Okay. Let's do this. Let's name this guy. H3PO4. Is this an oxyacid?
Yes.
Yeah, it's got oxygen in it. So then we're going to do Rick ate him before he could bite us. So what's the name of that ion? Phosphate, right? Phosphate. So ate and ick go together. The other way you could think of it is I ate it and said ick because it was nasty. So phosphate. Now, sulfur and phosphorus do this. They put that OR or UR back in there. I think because maybe phosphoric acid sounds funny, so it's phosphoric acid. I really need to work on my penmanship. I do much better with an actual pen and paper. So H3PO4 is phosphoric acid because we identify that the PO4 is phosphate. What if we're given a name? Nitrous acid. Well, what do we change us to? Ite. Us and ite go together. So this is from the ion nitrite. So then let's write the formula for nitrite ion. It's NO2 minus. The negative charge tells us how many hydrogens to put on it. 1 minus charge, then you need 1 hydrogen, because the hydrogens are H+. So HNO2. Okay, that's enough to make you dangerous. So your book is, giving you this nice flowchart. Flowcharts work really well for some people. And if they work well for you, you're going to be able to figure that out. And here's an example of going through this to figure out what the names of these things are. We don't want to start that yet.